Welcome to video 8. Actually, let me make sure that that is the correct number. I believe that's correct. Yes, video 8. And as was mentioned in video 7, we're now ready to begin discussing two-dimensional problems. What I mean by a two-dimensional problem is one where the problem domain is not restricted to just one axis, like the x-axis, but instead is over a region in a plane, which we generally take to be the xy plane. So, for instance, we might have some arbitrarily shaped region like this, and I've shown we still have the idea of nodes when we tackle 2D problems. So I've drawn in a few nodes there. I have nodes, some nodes are on the boundary and some nodes are in the interior. Of course, generally we would also have some nodes down here. And for an rather arbitrarily shaped problem domain like this, that might be something that we'll tackle in the future. There are actually a lot of interesting topics that we can cover during the last half of the course, and that's one of them. But for right now, we want to be a little less general than that, just so that we get the idea of how to tackle problems of this nature. And so let's look here at this problem. This is what we will this is what your next computer project will be about, is the solution of Laplace's equation over a rectangular problem domain. Now I want you to look closely at what's going on here. We have the x-axis shown here, and this is the y-axis, and we're going to designate the length of the problem domain in the x direction as L sub x, and the length in the y direction is L sub y. And we will assume that we have notice that we have divided up this region so that we have uniform spacing in the x direction and uniform spacing in the y direction, so that we have a Cartesian type grid. Now, the spacing in the x direction we're calling delta x, and that will be L sub x divided by nx minus 1. And this is similar to the kinds of equations you've had before in our one-dimensional problems. And similarly, the spacing in the y direction will be L sub y divided by ny minus 1. And both of these are constants. However, these two constants don't have to be equal to each other. Generally, they will be pretty close to each other in value, but they don't need to be exactly the same. Now, since there are nx nodes in the x direction and ny nodes in the y direction, the total number of nodes now is nx times ny. So you can see right away, let me make the remark that you can see how the number of nodes now might be much larger than what we had in our one-dimensional problems. For instance, in our one-dimensional problem, it wasn't unusual for us to go up to 20 nodes for a problem in one direction. But now, if we have a problem where the problem domain is extending over a plane, we might have 20 nodes in each direction, so 20 by 20 would be 400 nodes. So you can see how the number grows rapidly, and in fact in 3 dimensions it would not be uncommon at all to go to 20 by 20 by 20, which gets you up to 8,000 nodes. So increasing the dimension of your problem domain generally dramatically increases the number of nodes in the problem, which means that the matrix size is larger, and also means that the solution time required for the problem is larger. Now, as we mentioned a moment ago, we're going to start off by just looking at Laplace's equation, del squared V equals 0. We know from the work we've already done that there are a number of other interesting equations that we might consider, but for right now, let's just look at that. But remember now that in 2 dimensions, del squared V equals 0 becomes the equation partial squared V partial x squared plus partial squared V partial y squared equals 0. As was the case in 1 dimension, we need to consider not only the differential equation itself, but also boundary conditions. And now this boundary, the boundary for this region, has 4 parts to it: the bottom, the right edge, the top, and the left edge. And a possible set of boundary conditions that we might have could look like this. Vx at x and 0, so that's the bottom boundary here where y is equal to 0. V is equal to 0 along that boundary. V is equal to the sine of n pi y over L sub y along the right boundary. V equals 0 along the top boundary, and V equals sine of m pi y over Ly along the left boundary. Now, of course, there are an infinite number of combinations of boundary conditions that we could use, but I've chosen this set of boundary conditions because it's relatively easy to find the analytical solution for this set of boundary conditions. And of course, as was the case before, it's nice if you can find the analytical solution, because then you have something to compare to once you have your numerical solution, and this will help you to determine if you have errors in your numerical solution. Now, let's talk for a moment about the numbering of the nodes. We could number the nodes in a random fashion, but of course that's going to be probably going to make things more complicated. But if you want to number them in an orderly fashion, there are still a couple of ways you might go. You might number first along the vertical direction here, like this. You might start at 1 and then go up to 2, 3, 4, and then 5, 6, 7, 8. Or you could number first in the horizontal direction. And that's what we've chosen to do in this example, is we've numbered in the horizontal direction first and then in the vertical direction. So this is 1, 2, 3, 4, 5, and 6. And then 7, 8, 9, 10, 11, 12, 13, 14, and so on. Now, before we go any further, as you probably already imagined, you're going to want to write your code so that Lx and Ly can be chosen arbitrarily, and likewise so that Nx and Ny can be chosen arbitrarily. So just keep that in mind. But now, let's suppose that this is some node in the mesh, node I, and because of the way that we're numbering it, then you can see that the node just to the left of that will be node I minus 1. The node just to the right will be node I plus 1. And then since there are nx nodes in every row, the node just below that will be node I minus nx. And the node just above it will be node I plus nx. And notice that we need to know the node numbers for all 4 of these surrounding nodes, because when we write the expression for the partial derivative of v at node I, the partial derivative in the x direction, then we need to know the nodes to the right and left. And when we write the expression for the partial derivative in the y direction, we need to know the node numbers for the nodes to the top and bottom of this node. So that's why we need to go ahead and identify from the very beginning, once we're at a node, what the surrounding nodes are to the right, to the left, to the above, and below. Now let's see what we do with this. See, what we're trying to figure out now is as we fill the matrix for this for our problem, what numbers do we put in each row of the matrix? And I'm trying to help you out with this now. Okay, so the first thing we note here is, well, what if I is less than or equal to nx? Well, if I is less than or equal, if the node number is less than or equal to nx, that means that we're talking about a node here on the bottom boundary of the problem domain. And remember that for the boundary condition that we wanted for the bottom, as you can see right here, is v is equal to 0. This is a Dirichlet boundary condition. This is just exactly the same kind of boundary condition that we've always had in our one-dimensional problems at x equals 0. And just as was the case in those problems then, it's real easy to handle that kind of a boundary condition. What we'll have is that all of the matrix elements in that row will be 0, except for the diagonal element, and the diagonal element will be equal to 1. And the right-hand side for that row will be 0. Why? Because the boundary condition is v equals 0. If the boundary condition were v equals, let's say, 5, then r sub I would be equal to 5 down here. But since it's v equals 0, we have r sub I equals 0. Okay, now let's go to the next possibility. It says if I is greater than nx times ny minus 1. What nodes are those? Well, if you look at it for a moment, you'll see that those are the nodes along the top of our problem domain. And there too, we had the Dirichlet boundary condition, v is equal to 0. And so we do the same kind of thing for those nodes. All the elements in that row of the matrix will be 0, except for the diagonal element. The diagonal element will be equal to 1, and the right-hand side will be equal to 0. So that takes care of the top boundary and the bottom boundary. Now, let's proceed. It says if I minus 1 is a multiple of nx. Well, if I minus 1 is a multiple of nx, let's think about that for a moment. That would describe the nodes along the left boundary. And remember, along the left boundary, we had the boundary condition that v is equal to sine of m pi y over ly. By the way, m and n are also parameters that you need to set, to be able to set, and in fact to be able to change, and so you should set them at the beginning of your program. So if you're thinking ahead, you need to have lx, ly, nx, ny, and m and n. All of those should be parameters that you set at the beginning of your code. So now for that left boundary, again, all the elements in that row will be 0, except for the diagonal element. It will be equal to 1. But now the right-hand side is not 0 as it was for the top and bottom, but it will be sine of m pi y of I over ly. You need to pick the appropriate y, and so you need to pick the y for the node in question. Otherwise, this is really straightforward. And the same kind of thing happens here for the right boundary. It says if I is a multiple of nx. Well, if you think about it for a moment, you'll see that I is a multiple of nx describes the nodes on the right boundary. And for those nodes, again, we had the boundary condition, as you can see up here, v is equal to sine of n pi y over ly. And so we come down here, and all the elements in that row of the matrix will be 0, except for the diagonal. The diagonal will be 1, and the right-hand side will be sine of n pi y of I over ly. And so these four conditions you can code this into your or put this in your computer code very easily, these four cases, and these four statements will take care of all of the boundary nodes. And then for all other i's, well, if the node number is anything other than those four possibilities, then it must be an interior node of the matrix. And at interior nodes of the matrix, as we've already said, we want to have Laplace's equation, which in two dimensions becomes this: partial squared v partial x squared plus partial squared v partial y squared is equal to 0. And as we observed before, the partial derivative with respect to the second partial derivative with respect to x will be a v of I plus 1 plus v of I minus 1 minus 2v of I over delta x squared. And that's because the node to the right is vi plus 1 and the node to the left is vi minus 1. And the second partial derivative with respect to y will be v of I plus nx plus v of I minus nx minus 2v of I over delta y squared. And similarly, the reason for that is that the node above node I is node I plus nx, and the node below node I is node I minus nx. So that's how we get that expression. And we set those, the sum of these two expressions equal to 0. And so if you look at this, what this implies about the matrix, it means that in row I, now this is provided now that I is not a boundary node. If it's a boundary node, we go up to one of those four conditions up here. But if I is an interior node, then this equation tells us that mi I minus nx would be 1 over delta y squared because of this term right here. M of I minus 1 would be 1 over delta squared because of this term right here. M of I would be minus 2 over delta squared minus 2 over delta y squared. And here's the minus 2 over delta x squared, and here's the minus 2 over delta y squared. M of I plus 1 would be 1 over delta x squared because of this term. And finally, M of I plus nx would be 1 over delta y squared because of this term right here. And so that pretty much takes care of all the details about the numerical solution. And so your job now will be to write a code to find the numerical solution of Laplace's equation over a rectangular domain. And once again, one final time, here in this picture, you need to be able to easily vary Lx, Ly, n, m, and also nx, which is the number of nodes in the x direction, and n sub y, which is the number of nodes in the y direction. Now let's go ahead and talk about the analytical solution for this problem. The analytical solution is obtained. We're going to use something called the separation of variables technique, which is a technique that I think that all of you have probably seen before. So here is a reminder of what the problem looks like right here. We have sine of n pi y over Ly is the boundary condition on the right-hand side. Sine of m pi y over Ly is the boundary condition on the left-hand side. V equals 0 on the top, V equals 0 on the bottom, and Laplace's equation in the interior. The first step in the separation of variables technique is to assume that our solution, v of x, y, can be written as a function of x multiplied by a function of y. This is not always going to be the case, but it is frequently the case in problems of interest in physics and engineering. And so, and as we will see, this assumption will lead to a great simplification in the problem. So that's why we're going to go ahead and proceed with this. So if we substitute this expression for v into Laplace's equation, here's Laplace's equation, which when we expand out del squared becomes this. And now if we substitute this for v here and here, well, notice when you plug a of x, b of y in right here, since this is a derivative only with respect to x, the b of y can come outside. So we have b times partial squared a partial x squared. And similarly, when we substitute a of x times b of y here, since this is a derivative only with respect to y, the a term can come outside, and we have a times partial squared b partial y squared. Now the next thing we note is that a, as is written up here, a is a function of x alone, and b is a function of y alone. So really this partial derivative here of a with respect to x just really is an ordinary derivative, because a is a function only of x. And similarly right here, this partial derivative of b with respect to y is just really an ordinary derivative of b with respect to y, again because b is a function only of the one variable y. So we have this. Now let's divide both sides of this equation by ab. Or in other words, we multiply both sides by 1 over ab. So that's what we have here. 1 over ab times the left-hand side is equal to 1 over ab times the right-hand side. And so when we multiply this out, of course, on the right-hand side, we still get 0. On the left-hand side, we have this. And now if you bring over this 1 over b times d squared b dy squared term over to the right-hand side, we have this. So we have 1 over a times d squared a dx squared is equal to minus 1 over b d squared b dy squared. This is, we have achieved the separation of the variables. We've separated the x variation of this problem from the y variation. Now, the important thing to note here is that the left-hand side of this equation is only a function of x, and the right-hand side is only a function of y. Now, let's think about that for a moment. This equation, just like our original differential equation, Laplace's equation, was true everywhere in the interior of this problem, so must this equation be true at every point in the interior of the problem. So let's choose an arbitrary point, and let's think about the implications of this equation. Now, as we move back and forth on a horizontal line through this point, notice that as we move back and forth, y is not changing. And therefore, since the right-hand side is a function only of y, the right-hand side is not changing at all as we move back and forth along this horizontal line. However, you would think that the left-hand side would be changing, because as we move back and forth along this horizontal line, x is changing. However, the left-hand side cannot change, because if it did, then the right-hand side would have to change, but the right-hand side cannot change because y is not changing. And so therefore, we conclude that both sides of this equation must be constants. Likewise, you can think of this by looking at a vertical line through the point. It looks like along a vertical line that the right-hand side would be changing, but along a vertical line, x is not changing, and therefore the left-hand side cannot change. And so we conclude that both of these must be constants, and of course, since it's equal, they must be the same constant. So minus 1 over b d squared b dy squared is equal to 1 over a times d squared a dx squared, which is equal to some constant. And that's what we have here, and we're going to call that constant p squared. And if you wonder why it's squared, you'll see that algebraically this is going to work out nicely if we choose the constant to be p squared. So if we now break this equation here, this 1 over a d squared a dx squared is equal to minus 1 over b d squared b dy squared is equal to p squared. That can be broken up into what are the so-called separation equations. 1 over a d squared a dx squared is equal to p squared, minus 1 over b d squared b dy squared is equal to p squared. And so now what is so remarkable about this and so important is that what we have done, what we've accomplished, is that instead of having Laplace's equation, which is one partial differential equation and two independent variables, we now have two ordinary differential equations. And of course, we have a lot of experience in solving ordinary differential equations, and so we prefer that. Which separation equation should we tackle first? The one with the most homogeneous boundary conditions. And since both of the boundary conditions in the b direction are homogeneous, let's consider equation 2 first. Now, what do we mean there? Let me make sure you understand that. Remember, in our problem domain, right up here, you see the boundary conditions in the y direction at the top and bottom. Both of those are homogeneous. In other words, homogeneous, remember, means v is equal to 0. So that's 0 and that's 0. And both of these are non-zero, so we want to do the y equation first, and then come back to do the x equation. So we come down here. The equation in the y direction is minus 1 over b d squared b dy squared is equal to p squared. Oh, and by the way, before I go any further, I don't expect you to be able to reproduce this work on the separation of variables technique. I'm just showing you the details just for the sake of completeness so that you understand how it's done. But if you want to just jump down to the end where I give you the analytical solution, that's perfectly fine. Okay, so to finish this discussion then, here is our equation for b, which can be rewritten like this. And remember that at y equals 0 and also at y equals ly, b is equal to 0 at both of those, because we have that homogeneous boundary conditions at both top and the bottom. This is an ordinary differential equation. Is homogeneous and has constant coefficients, and so whenever you have a differential equation of that type, it will be profitable to you to assume a solution of the form ce to the lambda y. And so if we do assume a solution of that form, and then we plug into this equation, okay, we need to find out what to plug in for the second derivative. The first derivative of ce to the lambda y would be c lambda e to the lambda y, and the second derivative would be c lambda squared e to the lambda y. And if we plug that in for the second derivative and plug in ce to the lambda y for b, then we get this equation right here. And if we factor out the ce to the lambda y, we get this: lambda squared plus p squared times ce to the lambda y is equal to 0. Now, for this to be true, either lambda squared plus p squared must be 0, or ce to the lambda y must be 0. Now, we don't want ce to the lambda y to be 0, because if that's 0, then notice that ce to the lambda y is b. And so this would mean that b was 0. But remember, if b is 0, well, we come back up here. V is equal to a times b. And so if b is always 0, then v would always be 0. And so we have the 0 solution for our problem, and that would not match up at the right and left boundaries. So therefore, we reject the possibility that b is always equal to 0, which means we reject the possibility here that ce to the lambda y is always 0. And so if this can't be 0, then we must have lambda squared plus p squared equals 0, as we've written here. And that implies, of course, that p squared is equal to negative lambda squared, and or lambda squared is equal to negative p squared. So lambda is plus or minus ip. And you can go through the different possibilities here for lambda squared is less than 0, lambda squared greater than 0, or lambda squared equals 0. And what you'll find out if you go through these, I won't show you all the details here, but you will conclude that the only possibility that is reasonable for this problem is lambda squared is less than 0, which would mean that p is a real and positive, and in that case the solution here, instead of writing the solution as ce to the ipy, C1e to the IPY plus C2e to the minus IPY. Well, here it is, right here. The solution can be written in this form, but when P is real and positive, we generally instead will write it, the solution in this form, is K1 sine of PY plus K2 cosine of PY. And you've actually seen that already in one of the earlier computer projects we did. And as I said, cases 2 and 3, you can go through these, but you'll see that both of those are rejected. And therefore, we only have case 1 right here. Case 1 yields the only solutions. So we have b of y is equal to k1 sine py plus k2 cosine py. Now what can we say about p? Well, remember that we had two boundary conditions. B has to be 0 at the bottom of the domain, and when y is equal to 0 at the bottom, and when y is equal to ly at the top. So the fact that b is equal to 0 when y is equal to 0, b of 0 equals 0, implies, notice if we plug in 0 here and here and here, then the sine of 0 is 0, so this first term would drop out, and we get 0 is equal to k2 times the cosine of 0. The cosine of 0 is 1, so we get 0 is equal to k2. So the k2 term is 0 because of the boundary condition on the bottom of the problem domain. And so that gives us b of y is equal to k1 sine py. And now we need to apply the boundary condition at the top of the domain. B of ly is equal to 0. So if we plug that in here, then we get k1 sine of p times ly is equal to 0, which means either k1 is equal to 0, and we don't want that possibility because that would make b equal to 0, and we already know, we discussed before, if b is equal to 0, then our whole solution is 0, so we don't want that. So the other possibility is sine py, sine of p times ly is equal to 0, and that means that p times ly is k pi, where k is a positive integer, and so p is equal to k pi over ly. So our final conclusion is that b is equal to k1 sine of k pi y over ly. That is b. And now that we have found p, this is also relevant to our equation for a. So we stick in the value for p into our equation for a, and we get this. And this can also be solved by assuming, just as we did for b, we assume a now is equal to c1e to the, we can maybe call it s times x. And so when you make that assumption, Okay, so let's see here. I've lost my cursor. Sorry for the delay, but I've lost my cursor here and don't have my pen with me, and so I was stuck. Good. There. Now I have my cursor back. Okay. So when we stick in here to the equation for A, we get, and then we get this differential equation right here, and then assume a solution of this form, and so we arrive at this possibility. We can write the solution like this, and or we can write it in terms of sinh and cosh functions, and in the case that we're doing right now, it's more convenient to use the sinh and cosh functions, so I'll write the solution like this for A of x. And here's a brief refresher on the properties for the sinh and cosh function. And so a lot of the material here is just, to be honest, it's getting a bit beyond what you need. This is talking about how we put together these solutions. Okay, so now we get back here. I'm going to skip that material because it's not really very important unless you want to know every single detail of the analytical solution, and I don't think that's very important for us. So here I'll remind you of the solution we found for B is k1 sine of k pi y over Ly, where k is any positive integer. And A of x could be written either in this form or in terms of sinh and cosh. And remember that V is equal to A times B. So if we use the upper expression for A, we get a solution of this form. If we use the lower expression for A, we get a solution of this form. And now to finally wrap this up and find out what K and what the C's and or the D's are, let's look at our problem domain again. And what we'll do is, as I've already hinted, we're going to use that second form of the solution. So we're going to use this d1 sine of k pi y over Ly times the sinh of k pi x over Ly plus d2 times the sine of k pi y over Ly times the cosh of k pi x over Ly. And now we need to know what is k, and we need to know what d1 and d2 are. And so we see that the fact, remember that along the left boundary, okay, along the left boundary, we have V is equal to 0. And along the left boundary, okay, let's see what happens. When x is equal to 0, when x is equal to 0, the sinh of 0 is 0. So along the left boundary, this term will go away. And the cosh of 0 is equal to 1. So along the left boundary, in other words, when x is equal to 0, this just becomes d2 sine of k pi y over Ly. And that's what we have right here. d2 sine of k pi y over Ly. And that must be 0. Which implies that d2 must be 0. Which implies now that our expression for v is even simpler. We just have d1 times the sine of k pi y over Ly times the sinh of k pi x over Ly. And we want to choose d1 and k. Those are the only two things left. Remember, everything else is dictated by the problem geometry itself. Lx and Ly would be dictated, but we want to choose d1 and k so that we can satisfy our boundary conditions. And so what we will do, in order to satisfy the boundary condition at the left-hand side, which is that v along the left-hand boundary is sine of n pi y over Ly, we can satisfy that by choosing d1 to be 1 over sinh of n pi Lx over Ly. But then we also have to satisfy the boundary condition on the right-hand side, and that's discussed right here. And so when we put all of this together, here is our final solution right here. We get, and let me read this to you to make sure you can read it and you have no questions. V at an arbitrary x and y is equal to the sine of m pi y over Ly times the sinh of m pi Lx minus x over Ly divided by the sinh of m pi Lx over Ly plus the sine of n pi y over Ly times the sinh of n pi x over Ly divided by the sinh of n pi Lx over Ly. Now let's check this. It's easy to see, actually, that this satisfies Laplace's equation everywhere in the interior of the problem domain. But let's make sure that it satisfies the boundary conditions. Okay, remember, at x equals 0, we should have 0. Is that going to work out right? Well, at x equals 0, if x is equal to 0, then this would become sinh of m pi Lx over Ly. And here we have sinh of m pi Lx over Ly. So these two terms would cancel. And at x equals 0, the first term would just be sine of m pi y over Ly. And, I think I said something incorrect there. At x is equal to 0, what we want, here's right here. At x equals 0, we want this, sine of m pi y over Ly. And so, as we just showed, or as we just discussed, at x equals 0, this term will cancel this term, and indeed we will get sine of m pi y over Ly. And notice the second term, since sinh of 0 is 0, the second term drops out entirely. So the boundary condition along the left-hand boundary is indeed satisfied by this expression. What about the boundary condition at the right-hand boundary? At the right-hand boundary, we're supposed to have sine of n pi y over Ly. Well, let's see if we'll get that. At the right-hand boundary, x is equal to Lx. Okay, x is equal to Lx on the right boundary. So this becomes sinh of 0, which is 0. So this term will drop out. And when x is equal to Lx, we get sinh of n pi Lx over Ly, sinh of n pi Lx over Ly. These two terms cancel, and indeed we're left with sine of n pi y over Ly. So this expression definitely satisfies the boundary conditions in the left and right. What about on the top and bottom? Well, on the bottom, y is equal to 0, and the sine of 0 is 0, so this would go away, and likewise this would go away. So this is definitely going to satisfy the boundary condition on the bottom as well. And the only remaining question is, does it satisfy the boundary condition at the top? Well, on the top, y is equal to ly, and when y is equal to ly, this becomes sine of m pi, which is 0, because m is an integer, and this becomes sine of n pi, and again, n is an integer, and so that will go away. So this expression, this total expression right here, it satisfies all the boundary conditions, and it also satisfies, in the interior, it satisfies Laplace's equation, and therefore this is the analytic solution for this problem. And so, again, what you want to do is to write a computer code for which m, n, lx, ly, nx, and ny are treated as parameters that can be varied from one time to another, and you will show what you want to do is to produce a table showing the numerical solution and the analytical solution at all the nodes in the mesh, and we'll also calculate a error where the error will be defined just as we did it for the 1D case. So that's the computer project that you will work on next, and that concludes video 8. So good luck.